Hello.
Fine? Okay. Start? Okay. So let me start today again with just as usual a brief recap, just so that we are all same page of what we did yesterday. So what we are looking at is the statistics of the maximum of a random walk of n steps, where the position of the walker, remember, it was evolving by this Markov jump process, where these are IID random variables, each drawn from f of eta. So we have this picture, and we assume that x0 equal to 0. You start from the origin. You go up to n steps, and we are interested in the random variable x max, which is the maximum. Okay, and what we said is that is easier to calculate the cumulative distribution of the maximum, which we are writing as, okay, some level A up to step n. So this is the probability that the maximum is less than the height A, and we are denoting it by this notation q a comma n. And again, if we know q a n, we could derive by taking derivative with respect to a, we can get the PDF of the maximum. But this q a n, we said that if we make the transformation, that means I shift the origin to A and look in the downward direction, then this is like another walk, same walk basically, and here it's 0. So as if it's starting at the initial position A, so this is, if you like, the probability so the maximum A actually gets becomes the initial position under this reflection. Starting at A, probability that the walker stays positive, because it stays below the level A, which means once I reflect, it just becomes stays positive up to, and this is just for simplicity, I mean, up to step n. Okay, and then we said that this object, if I define this restricted Green's function of going from initial position, let's say x naught equal to A up to n, so that means if I reach the final point x at step n, then I have to integrate over the final position from 0 to infinity, because it cannot go to the negative side. So this is just the integral of this from 0 to infinity. So the basic object was this restricted Green's function, and this restricted Green's function was satisfies this integral equation where you say x prime is the position at step n minus 1, and n, little n is the running index. In the end, you will put little n equal to capital N. So after n minus 1 steps, I reach at x prime, and then I make a jump. Okay, and starting from the initial condition, so one thing I should say, which I didn't say yesterday, is that when you have an integral equation like this, you don't have to specify boundary condition. If I just give you the initial condition, so you can calculate G1 after first step just by putting this and integrate. You can calculate G2 by putting G1 and recursively like that. So you do not need any boundary condition at x equal to 0, basically. Okay? You need that for differential equation, not for integral equation. Okay? So this is an important point. And then we said that in general, it's very hard to solve this integral equation for arbitrary jump distribution of f of eta. There is a complicated formula, this Ivanov formula or Polacek-Spitzer formula, and so which has a complicated expression and so on. But there is one interesting result, which was if you take q of 0n, so that means what is the probability that starting at the origin, so origin is a special point, starting at the origin, it remains positive up to step n. Okay? And that from general result of the Polacek-Spitzer formula, we showed that this Q0n actually has an universal result, and this is the Sparr-Anderson theorem. And this result is true for, it's universal for any n, and it's true for example, uniform Walker or Gaussian Walker or exponential jump distribution, or even for Levy flights. Okay. So even for Levy flights, this is true. And what you see, just using Stirling formula, that in the large n limit, this decays like square root of pi of n. So there is survival probability, if you like, starting at the origin. As you increase n, it becomes increasingly difficult to survive, and it decays as 1 over square root of pi n. In particular, when you take very large number of steps, the survival probability goes to 0, which means that it definitely comes back to the origin at some point. Maybe it takes a long time, but it does definitely. The fact that it goes to 0 as n goes to infinity means it cannot survive forever. Okay, so it has to cross the origin, and this is something what is called the recurrent property of one-dimensional random walk. Recurrent means with probability 1, it will come back to the origin. It cannot it cannot survive forever, basically. Okay, so this result is actually very important. We'll see later. We'll actually use this result for other things, and I'll come back to that at some point. So, and I also mentioned that there is one special distribution, which is the double exponential distribution. If you take f, another solvable example. Not another, one solvable example. Case is when you take f eta to be half e to the power minus mod eta. Because then, as we showed yesterday, that you could reduce this integral equation into a differential equation, and you can actually solve the result. I didn't give you the solution, but okay, that's a little bit details you can find in the book if you like. So today what I want to do first is another solvable limit. Solvable case. This is the continuous time limit or Brownian motion. So as I explained to you that such a continuous time limit exists provided this sigma square, the variance of the jump, this is symmetric distribution, so this is second moment itself is the variance. So as long as this quantity is finite. If this is infinite, like for example Levy flights, there is no obvious continuous time limit. Okay? So let's assume now that the jump variance at each step is finite. So for example, in this class you can have exponential jump distribution, Gaussian, uniform, etc. And I will also assume that it's a continuous distribution, the PDF of f of eta, CDF of f of eta, cumulative distribution, which means that it excludes the lattice random walk. Lattice random walk is a bit special because there are lots of delta function jumps. So I'll evict that. Otherwise, it's more or less symmetric and continuous distribution. Okay? So we'll assume that f eta. Okay, symmetric is continuous. I mean, it's a little bit of details, but let's say symmetric for the moment. Okay. So, and as I explained to you, that how do you go from the discrete jump process to continuous time limit? So you have to define, so your actual, in continuous time limit, your, steps is not defined, it's a time really, real time. And here it's a steps. So what we do is that we make a time step of length t, so that n delta t is actually t. And then you have to take the limit delta t goes to 0. But then we saw that if I look at the variance of the position after step n, so this was exactly n times sigma square in the discrete process. So if I want to do the continuous limit, so I have to replace this n by t by delta t and sigma square. So to make this of order 1, you must take sigma square proportional to delta t. So when you take the delta t goes to 0 limit, in order to have a continuous time limit, I must take the jump. It cannot have a very big jump. The jump also should go to 0, variance of the jump, and it should go to 0 exactly as linearly in delta t, and that proportionality constant is what is called the diffusion constant. This is, as I said, this is the Einstein result. And if we do that, then this process in the discrete time, it goes to the Brownian motion, where this eta of t is now a Gaussian white noise. With a 0 mean and a correlator, which is a delta function correlator, delta of t prime. Okay? And moreover, this equation here, which is discrete case integral equation, and we said that this integral equation, so again discrete, yeah. Why is the noise Gaussian? Because when you take the delta t goes to 0 limit, okay, you have your discrete process, right? So of course the discrete, the eta is not Gaussian in general. But when you take this limit properly, you calculate the Fourier transform of the noise, and just like we proved the central limit theorem, you see that when the delta t goes to 0, all the higher cumulants also goes to 0. So as a result, the eta, whatever noise you started with, as long as it's finite variance, effectively it goes to a Gaussian distribution, but with a delta correlator. Okay? So the integral equation for this guy, this is our restricted propagator, right? This is the basic object we need. So, so that becomes a differential equation for okay, and how to derive this differential equation? You remember I did it in the class. You just say This is the previous time step. So if this is t plus delta t, this will be at time t, and then at time t, it must have been at x minus the eta times delta t, and then you do a Taylor expansion of that and take the limit delta t goes to 0, and then this integral equation reduces to the diffusion equation. Okay, so this is a partial differential equation. And it's valid because you started out, so essentially what we have, the process, the discrete time random walk process, now you have a continuous time process. You start at x0 and you have a Brownian motion. So this is time. So basically that process there, you take the delta t goes to 0 limit, it becomes very jittery. So it's a process. So this is the limiting process. This is the Brownian motion. You've seen that by central limit theorem, this process just converges to a Brownian motion. So this is the Brownian motion trajectory. And this is a very jittery process in the sense that the derivative, because its derivative dx dt is noise, and noise itself has delta function correlator, so the derivative doesn't really exist. But the process makes sense, it exists. If you calculate the x squared at any given time, so that will be 2 dt for an infinite process without boundaries. Okay? So now we are looking at, to calculate the restricted propagator, we are looking at this same diffusion equation, but now it's valid only for x positive because you don't want the path to cross the origin. Okay? So the analogous quantity, what we called QAN there, so that here just becomes Q, let's say A, okay, I call it x0 equal to A, comma T. So this is the survival probability of the particle. That means starting at x0, what is the probability that the walker, the Brownian walker now, it stays positive up to time t. So the n here just gets reflected to t. Okay? And just like this equation here, this integral here, so we can say that if I know the restricted propagator, so I just have to integrate the final position x from 0 to infinity. So the program is clear. So I have to solve this differential equation, get the solution in the upper half space, get the solution, and then integrate the final position. That gives me the survival probability. Okay? So it was very difficult to compute here because it was just a polar J pizza solution, but you'll see that in the continuum limit it becomes much easier. We can calculate this explicitly. But there is one crucial point here, which is that, as I said, this is an integral equation. Here I did not need any boundary condition at x equal to 0. Okay? I can just iterate the solution and it auto determines this itself, the solution. But here it's a partial differential equation, and partial differential equation or a differential equation in general, you have to first specify the domain where this equation holds, which is in the upper half plane. And then you have to then specify what are the boundary conditions, because if you don't specify the boundary conditions, there is no, the problem is ill-defined. Okay? So what is the boundary condition here? Okay? So I have to, supply the boundary conditions. So what are the boundary conditions? So one boundary condition is clear. So if I take x goes to infinity limit, so my domain is 0 to infinity. So I have to specify the boundary condition at infinity and at 0. So if I take x going to infinity, that means I'm asking what is the probability that starting at x0, it arrives at infinity at time t without crossing the origin. But that's not possible because if you start from here, if the time is finite, it cannot arrive at infinity in finite time. Okay? So therefore, this probability must be 0. So that's one boundary condition. And the second boundary condition is a little bit tricky. So which is at x equal to 0. And this will also be 0. Why? Because you're asking that, I mean, there could be many trajectories. Some of them will cross the origin. If you look up to time t, there could be many trajectories. You might arrive here, you might arrive here. So out of all possible trajectories, this is the x, so you fix x naught and x. You're asking if it is a free problem without the boundary, then you could reach there like this. Many possible paths arriving that, right? And out of all many possible paths, what you want, your restricted propagator, that means you are asking for the probability, you have only those fraction of paths that stays positive all the way up to t. So these two paths are allowed, but this is not allowed, this is not allowed because they have crossed the origin. So you want to somehow, not count those paths which have crossed the origin. So how can I implement that in a differential equation? And that is implemented by this, it's called the absorbing boundary condition. So what it says is that at any time t, I'm just implementing by hand that the probability that it arrives at the origin is 0. Because if I do that, that means I'm just putting that it cannot arrive at the origin, because if it has to go to the negative side, it has to go through the origin. So if I forbid the path to come at the origin, then that automatically counts only these paths that have not crossed the origin. Okay? So therefore, you have to solve this problem on the upper half plane, x positive, with these two boundary conditions and the initial condition, which is as before. Because initially at time t equal to 0, it was at x naught, so therefore this, and this must be, this is because it starts from here. So at time t equal to 0, it cannot go anywhere, so it must be only at x naught. So therefore this is the initial condition. So that fully, defines the problem. So you have a partial differential equation in a given domain. I have given you supplied you the boundary conditions. I have supplied you the initial conditions. So there must be a unique solution to that problem. Okay? Yes. Can you speak loudly a little bit? Yeah. It cannot. In a continuous time limit, Brownian motion is very jittery. So what you can show that if it comes to the origin, it has to cross infinitely often the origin before it goes away. Okay. So in fact, the density of 0 crossings is actually infinite. So Brownian motion, you can do a simulation by yourself to check this. It's a very interesting thing. That Brownian motion property is that if it crosses the origin, it crosses infinitely often. And if you actually you can calculate the density of zeros, density of zeros actually goes to infinity as 1 over square root of delta t. Okay. So that means you cannot, say that, it just came and touched and went back. So there is no grazing trajectory. Okay. It has to cross. Okay. And therefore, if you implement this boundary condition, that automatically restricts only to walkers that did not even arrive at the origin. Okay. You should remember this result, we'll need that later. And I'll also give you a simple proof of that result later. Okay, so our problem is clear. So this is our equation, PDE, and these are the two boundary conditions, and this is the initial condition. So how do I find the solution? So there are many ways to find the solution, but simplest physical way, I mean, you can do it by Laplace transform with respect to time t and then solve the boundary value problem. But simplest way is to invoke sort of physical solution, which is what is called by method of images. So this is an idea that is borrowed from electrostatics. So what's the idea? So I'm looking for first the solution of this. Okay. Now I have shown you that if you have a free space, no boundary, this is an unrestricted propagator. Then you can just take Fourier transform because it's infinite space, and the solution, very general solution, okay, is starting from y, what's the probability derives at x, is this. Okay. So indeed, in the full space, so you can write down any solution. Let's say, I mean, forget the initial condition for the moment. I'm just writing down the very general solution that just satisfies this equation. Okay? So I can take any y. Okay? So y can be anything, and just put a weight factor. Suppose I give you this function. Okay? So you can check if I just substitute it here. This satisfies this equation, right? Because not the initial condition, but I mean generally this is a general solution because this is just a core solution, basically bare Green's function solution. So you just substitute this because if I take just operate del t minus d del x squared on this guy. But this, you can check by direct calculation, no matter what the value of y is, this is always 0. Okay? So therefore, this is also 0. So any solution, I can always write it as a linear superposition of these guys. So this is a linear . And now the trick is that this is in the full space. So you are looking for solution which is only in the half space. So main thing is that by inspection, can you find out, so you can choose whatever gy you want. Okay, so you want to find out some gy such that it satisfies, the solution satisfies this boundary condition as x goes to 0 and x goes to infinity, and also the initial condition. Okay. And this is the method of images because, okay, first I'll tell you why. So let's choose. I know the solution is unique, okay, given the boundary condition. So I just have to find out, can I find some appropriate choice of gy such that I can satisfy both boundary and the initial conditions. So now I'm giving you the solution. Suppose you choose this. Okay? Then my claim, I'm saying that if I now calculate with this gy, So I'm just constructing a solution, and then we'll check that it satisfies the boundary and initial condition. Only thing I know is that this guy here is a solution of the differential equation, because we just said this is a general solution, right? Now, if I choose this, and I'll discuss in a minute why is called method of images. So then I have to do the y integral. So what you find is that okay, so this is the solution. Now let's check. We already checked that it's a solution of this differential equation. And now I say that I construct this solution. I say that now I'm claiming that if I restrict by x to be between 0 to infinity, then this is the unique solution of this differential equation. So first of all, it's a solution of the differential equation, okay, for x in the 0 to infinity. Next, I have to check the boundary condition. When I take the x goes to infinity limit, both terms individually go to 0. So it satisfies this boundary condition. When I take x equal to 0, you see this e to the power minus x naught square over 4 dt minus the same quantity, x equal to 0. So it does satisfy this boundary condition as well. So it satisfies both boundary conditions. What about the initial condition? So if I take t goes to 0, t goes to 0, this object here goes to delta function of x minus x naught. This you can check, because diffusion equation, you know that initial condition was, this is like an initial condition starting at x naught. So therefore, this is this minus delta of x plus x naught. But since I'm restricting my x to be between 0 to infinity, this is, since x naught is positive, you know, I started from x naught positive, right? This is the origin. So this is never going to be satisfied, equal to 0 for all x positive. So therefore, this is just delta of x minus x naught. Okay? So by inspection, we found a solution which is a solution of the differential equation. In addition, it satisfies the both boundary conditions and it satisfies the initial condition. Therefore, this is the solution, unique solution. Okay? Now, what does this mean, this choice? So it's like you have the origin here. So you are looking for solutions in the upper half space, right? X positive. You're looking at all the trajectories that go, and such that this thing vanishes exactly at the origin. So what you do, you put in, it's like exactly like in the electrostatics. So you put an image charge at minus x naught, if you like. So that corresponds to this guy here. This is like initial, starting at initial condition at minus x naught. So in the free space, so if you think of all trajectories that start from here, okay, and go up to time t, and all trajectories that come from here and go up to time t, and you take a linear combination of them but with a negative sign, so that they exactly cancel each other when x equal to 0. So this is exactly like electrostatics. Electrostatics, you know, I mean, if you remember that if I want to, you know, put a conductor, so there, of course, we solve this Laplace's equation. I'm looking for, I put a charge there, okay, some E, and I put a conductor here. So conductor means the potential on the conductor is 0. And so I'm looking for the solution. What is the potential at any point here? Okay, let's say in 3-dimensional space or something. So here we know that it satisfies the Laplace's equation, right? Because there's no charge density here. Actually, a Poisson equation, if you like, so delta function of x minus x naught E. Oops. So if I put a charge there, so this is my potential. If I put a conductor, that means potential is definitely 0, so I have to solve in the upper half plane. And there I know that the potential satisfies the Poisson's equation, this charge here. And I want to find out what is the value of the potential at some other interior point here, right? So I need to find the solution of that. And what we do, but that solution that has to, so I have to solve the Laplace's equation here with the boundary condition that phi equal to 0 here and phi equal to 0 as x goes to infinity. So to do this, what we do is exactly we put an image charge here so that the potential due to, at any point on this surface due to this charge and due to this charge, they cancel exactly each other. And then that constructs the solution for, so you just take a linear combination of the phi. So basically in 3 dimension, it will be like E by, let's say at any point here, if this distance is R1 and this distance is R2, then the solution potential, at this point R will be E over R1 minus, it's R1 minus E over R2. And exactly when you are on this line, they exactly cancel each other and you get a phi equal to 0. But this is, and the idea is the same because each of them individually satisfies the Poisson or Laplace's equation. And you take a linear superposition, since this is a linear operator, so therefore this is a solution. And you take a good right combination to satisfy the boundary condition. So it's the same, exactly similar idea. Here, of course, there's a T and all these things. But if you think in terms of operator, this is just this operator here instead of just Laplacian. But the same idea holds. Okay? So this is the solution. So then you are more or less done now. There are other ways of, one has to be a little bit careful because here we, found the solution by inspection and using ideas from electrostatics. But you don't need to do that. As I said, sort of more, if you don't know anything about physics and electrostatics, you would actually solve this equation. To solve that, you just take a Laplace transform with respect to t. That reduces in the Laplace space just an ordinary differential equation, boundary value problem, and you can find the solution quite easily also. And if you invert the Laplace transform, you come back exactly to this solution. But this is a sort of more physical way of getting it. Yeah. Yeah.
Which means to really once it touches the point, there's no next step.
Right.
So all directories vanish at x equal to 0.
All directories that reach at x equal to 0. So that means I'm just keeping, so I'm getting rid of those trajectories which have touched the origin or crossed the origin. So that means what is left, this g plus, if you integrate over x, it's not a normalized to 1. So that means this is just a fraction of trajectories that stay positive, basically. So that's the idea of this absorbing boundary condition. Okay, so we are more or less done. So I have explicitly this solution here. This is this guy. And I just have to calculate this survival probability. So Q of AT. A is just x naught basically, so I have to integrate over the final position. And this integral is very easy to do. You can do it by yourself or do by Mathematica. You find that this is error function of A over square root of 4 dt, where error function in my convention is defined like this. It's just the integral of Gaussian with variance half. This is just a definition. So this is so error function has this property, if you plot the error function of z, here of course A is positive, but so we have to look at the positive side, error function of z. So when z goes to 0, it goes to 0, and it basically goes to 0 as linearly, and then it sort of grows, and then it saturates to 1 as z goes to, when z goes to infinity, you can do this Gaussian integral, it's exactly 1, okay. So it does this. So it's linear here and then saturates to 1 as z goes to infinity. And in principle, you can do it on the negative side, it's an odd function, so it just goes like this. So that's it. So Q of AT, so therefore, what we have is the probability, this is our original problem, remember? We are asking for this Brownian motion, and we are asking what is the probability that the maximum, so x max up to time t, so this is less than some height a. That's a cumulative distribution, right? So therefore, probability that x max is less than equal to a up to time t. This is exactly this error function of a over square root of 4d. Okay? So this is my cumulative distribution, and therefore the PDF of x max, probability density function, so I was using this notation P max of a comma t. So this is just the probability density, probability that x max equal to a within time t. So this is just, as I said, this is just a derivative del a of this q of at. This cumulative distribution, I mean, you just have to take this is just the integral of the PDF, so therefore take the derivative. So if I take the derivative of that guy, so the answer is therefore 1 over square root of pi dt times exponential minus a square. So remember that a is positive. And a has to be positive because, if you start from the origin, start from, the position, I mean, because in my original notation, this is, again, here it's a starting point is a, but this is reflected work. But in the original problem, your Brownian motion is starting at the origin, and you are asking for that what is the probability that x max is less than equal to a. So that was this q of at. And this is the PDF. But you see, if the Brownian motion starts at the origin, I mean, its maximum value, cannot be negative, right? Because maximum value has to be at least 0. Because if it starts from here, I mean, worst case, it can just go all the way down. But if it goes all the way down, then its maximum value is 0. Okay, so maximum value can never be negative. So this distribution has support only on the positive a-axis. Okay? And you can check that this is normalized. Okay. So therefore, our goal is to compute, because Brownian motion is a special case of random walk, and but still very strongly correlated system. And we were interested in calculating the maximum. And you see, even for Brownian motion, this solution is not completely trivial. I mean, it requires a little bit of work. And so this solution here, so P max, I just want to write it in the same form that we are writing for IID variables. So this is not for large t, this is for all t in the continuous time limit. With a positive, so this is theta of a basically. So that means if I plot this function, so it starts at the origin, and it's a half Gaussian, so it's sort of goes down there. And the width of this goes like square root of t. You can calculate all the moments, but we'll do that in a minute. But first thing is that you realize that you can again, I mean, I don't want to write in the same scaling form that we're writing previously for IID variables. The BR stands for Brownian. So at different times, it will go like this. And sorry, this thing will decrease. It will become spreader bigger and bigger. But if you scale your x-axis a by square root of dt, they will all fall onto the same curve, and this curve is precisely this function here, which is a single function. So you see that this is certainly neither Gumbel nor Frechet nor Weibull. It's something very different. Okay? It's a half Gaussian distribution, and it's a bit non-trivial. I mean, the Gaussian it's not Gaussian. One has to remember that. So Gaussian and half Gaussian is not the same, because if you calculate, for example, you can calculate all the cumulants. Okay, so if I look at the kth moment of the maximum, so this is exactly x max to the power k expectation value of that, right? So this is the kth moment. So this means 0 to infinity a to the power k, and then p max of at dA. So I just substitute this guy and I calculate this, and you can check. I will not do the, but kth moment is given by 1 over root pi. This is the gamma function. Okay, so for instance, average value of x max. So this is the average value of the maximum up to time t. So that is just put k equal to 0, of course, is normalized to 1. So this is 1. You put k equal to 1, so you get square root of 4 dt over pi. You can calculate the second moment. So this means that the spread here, mean value of the maximum is going like square root of t, which is normal because if you have a Brownian motion, its typical position displacement is square root of t with fluctuation. So the maximum will be of the same order, but with a prefactor which is quite different from the usual 2 dt, square root of 2 dt is 4 d over pi. So the variance you can find by just putting k equal to 2, not variance, second moment. So second moment you can check that this is just 2 dt. Just putting k equal to 2. And therefore the variance of x max, which is so this minus that, this minus that squared. So this actually goes like 2 times 1 minus 2 over pi dt. So the prefactor here is quite non-trivial. It's not completely trivial. 2 into 1. You couldn't have guessed this without doing the calculation. Okay. So, but anyway, basically we know the full distribution. So therefore, this is one of the examples of, and in fact, I mean, since you know all the moments, you can calculate all the cumulants, and you will see that all higher cumulants are non-zero. It just shows that it is not a Gaussian distribution. Okay? It's a half Gaussian distribution. Okay? So this is the exact solution for the Brownian motion. So in that limit of random walk, continuous time limit of random walk for when the jump variance is finite. So this is one solvable example of a strongly correlated system where you can calculate the maximum exactly. And you see that the scaling function of the maximum is very different from the IID case that we have discussed before, which shows that the correlations do play a very strong role. Okay, and and this is also, you can see it has a wider universality in the sense, no matter which random walk you take, uniform or Gaussian or whatever, in the long time limit, when it converges to Brownian motion, in long number of steps limit, we showed that by central limit theorem that in large number of steps it converges always to Brownian motion. So therefore, this result is true for all such random walks. So their jump distribution might be different. Only thing that matters is their variance, sigma squared. And so essentially, so what it means is that, so let me just make this universality statement. So going back now to discrete time again. Yes. So yes, so because that, okay, that corresponds to putting a drift. Okay. So for the, yes. Yeah, so if you put a drift term, you can still calculate everything, okay? No, it won't come to this one, because when you put a drift term, you know, it sort of maximum, for example, it tends to, if you put a positive drift, it tends to go that way, right? And so this is known, actually, you can compute that, again by the method of images, but it's a slightly more complicated. I'm not going into that, okay?
But that also will have uniformity, like you're saying universality for different distribution and stuff.
Yes, so if you take a discrete random walk and you put a drift, then again in the large n limit, they all converge to Brownian motion with a drift. Okay?
That also leads to one uniform kind of universal.
Yeah, universal, but it won't be the same function because this is without drift basically. Okay? So, yeah.
Why can't we solve the fault formula for discrete time freely and then subtract the parts?
No, it won't work. You cannot do these things. No, because I mean, first of all, I mean, as I said, you know, for integral equation, you do not need even a boundary condition. So there is no need of a boundary condition. It's a recursion relation. No, combinatorial way, I mean, even if I told you that, you know, f of eta, if you take, I mean, the solution actually, one knows the solution, okay? And this solution is very complicated, this Polar-Pizza formula. So obviously the method of images and things like that will not work. Okay, that works only when you are able to reduce it to a differential equation with a boundary condition. Okay, so therefore it works only in the continuous time limit. Okay. So if we take in our discrete set of walkers, but with all, you know, such that this sigma square equal to jump variance is finite. So what I showed it to you before in the lectures, that for all such processes, xn equal to xn minus 1 plus eta n, such that sigma square is finite, then this xn, this process in the long time limit, it converges to the Brownian motion in continuous time, right? This is the statement of the central limit theorem, okay? So which means that for all such cases, and the connection between them is that this sigma square n goes to 2 dtt. Okay? So in fact, if you could compute the, you can check this, for example, numerically, that for the discrete process, therefore, if I take this guy, probability distribution of the maximum up to step n, and if I now take the n goes to infinity limit and a goes to infinity limit, but keeping a over square root of n fixed, then this will again converge to this scaling form, except that you have to replace dt by sigma square n by 2. But the scaling function is exactly same as in the Brownian motion, which is half Gaussian. Okay. So I can take any discrete process with a finite jump variance, uniform, exponential, Gaussian, whatever, and now I have to take the large n limit. For the Brownian motion, this was valid for all time t. But if I have to make the connection between the random walk and Brownian motion, I have to take the large number of steps limit, because only in the large number of steps limit it converges to a Brownian motion. Okay, so then, you know, then this is the result that you will get, and you can actually prove that rigorously also. But you know, basically whatever the Brownian motion result is there, you just replace dt by n sigma square, okay? And then you get the discrete answer. So therefore, what you see is that this particular fixed point, or if you like, Brownian fixed point, so this also has a wide, so this is the Brownian fixed point. Like those Gumbel, etc., etc. So here also there is a wide class of random walk problems, but the only thing that you require, you don't need the detailed knowledge of A theta. Only thing that you require is that the second moment is finite. So then up to the second moment, okay, so if you scale it out, but they all convert into the same scaling function, which is this Brownian fixed point. Okay, so they all flow into that. But of course, if sigma square is not finite, like Levy flights, we cannot use this. And Levy flight, one does not know really what the distribution of maximum is, because you could not really, use central limit theorem to make this connection to Brownian motion. Okay. So there is no continuous time analog of Levy flight. I mean, people write down sometimes, but effectively you still have to solve the integral equation. You cannot reduce to a differential equation. Sometimes people call it fractional differential equation, but that's not really useful in this context, at least for the boundary value problems. Okay, so this sort of concludes basically the one example. I mean, of course, there are other examples of strongly correlated system where you can actually compute the distribution of maximum. And for instance, I mean, I mentioned, I mean, I'll not do it in the class, I don't have time. But if you look at the, Gaussian random matrices, and if you look at the largest eigenvalue, for example, so one knows that the distribution of the largest eigenvalue, properly centered and scaled, is something which is called the Tracy-Widom distribution, okay? And it's a very non-trivial distribution. So that's like another fixed point, if you like, because the correlations there are quite different from the Brownian motion correlations. So it's not the similar type of correlation, but it's also strongly correlated system. So at this stage, we don't know really how many such fixed points are there in strongly correlated system, or are there some finite number of fixed points? We do not know that. And so this is where the field stands. I mean, it's right now, so what people do is solve different models to get some idea, but there is no general theory yet.
So that equation, if I add in the diffusion equation, double derivative in time.
Yes.
You have space, double derivative.
So it's a relativistic equation you are saying. Relativistic equation you are saying.
Or that they call telegraphic equation.
Yeah, telegraphic equation, yes.
Telegrapher's equation.
Telegrapher's equation, yes.
So is that also solvable?
Yes, telegrapher's equation, some things, I mean, so there's something called run and tumble active particle, okay? So this is exactly, basically satisfies telegrapher's equation, okay, where the noise has an exponential correlation. It's not, so basically you write down, so for example, if you take, so this is the run and tumble particle, run and tumble process. So here, it means dx dt, instead of Gaussian white noise, you just put a V0 times sigma of t. This sigma of t has nothing to do with this sigma. I mean, this is different noise. And this sigma of t is a telegraphic noise like this. So it's +1 or -1. And it switches from +1 to -1 at a constant rate, gamma. Okay? So you basically wait for an exponentially distributed time, e to the power minus gamma t, and then you switch to -1. And then again you stay negative up to some exponentially distributed random time, and then again switch like this. So in this case, so if you say this is your noise, and these intervals, as I said, they are distributed by exponentially with a mean, so this is called the inverse persistence time. So it persists up to time, typical time 1 over gamma. So this noise here, the difference with Brownian motion is that this noise, if you calculate this guy, is just V0 square times e to the power minus, okay, up to some constant, 2 gamma t minus t prime. See, there's a gamma here. Maybe 2 gamma. Something like that. So this is just a telegraphic process, and this telegraphic noise, if you calculate the correlation function, it's actually exponential minus 2 gamma t minus t prime. So that means it remembers the past. It's a non-Markov process. Okay, so it's correlated. Noise itself is correlated with its previous history, And it reduces to the delta function noise only in the limit when gamma goes to infinity. Okay? So if you take that means it flips all the time basically. So then the correlation becomes 0 and it becomes a delta function. And then it reduces, this process reduces to a Brownian motion. So if you look at the trajectory of this process, so essentially what it does, so this means this particle moves with a constant velocity, okay? And this velocity changes plus minus 1 like this, okay? This is what it does. So that's why it's called run and tumble, because bacteria often do this. They run up to a certain exponential time, and then they change direction.
Electrons also do that.
Electrons also do that, of course. No, I know. So this is the telegraphy, huh? Gamma is not there. Okay. Yeah, gamma will come this things, yeah. Okay. Whatever, some constant, up to some constant, yeah. So in the limit, when gamma goes to infinity, then effectively it reduces to, again, Brownian motion, okay? But because then again it sort of becomes jittery, very quickly it changes sign. But otherwise, this is a process which is different. And to calculate the maximum of this process is quite complicated. It's not that easy. Okay. Well, it is done in some sense, some moments are known. I mean, full distribution also you can calculate some ways. But it's not that trivial basically. Okay. It involves all kinds of Bessel functions and things like that. I mean, so it doesn't have a very nice scaling limit basically. Okay. But it can be done, yes.
So this continuous time, can we take it even if we have multiplicative time?
Depends on what kind of process you are looking at. Okay. Some multiplicative noise, you have to, you have to define properly. Okay. Multiplicative noise, you have to define whether you are doing it Ito sense or Stratanovich sense and so on. Okay. And then you can write down, for
This will be Ito sense, otherwise it won't be a Markov.
no, Ito sense is, no, don't confuse with Markov and Ito. This is different things.
Discrete time,
Yeah.
then you have to evaluate the noise at the initial position.
That's for Markov process.
For Markov.
But this is just additive noise. Here there is no question of Ito or Stratanovich. For additive noise, you don't have to invoke, it's just saying that, this is, at the current position, I just jump, okay. Ito and Stratanovich you have to invoke only when if you have an equation like this, dx dt is the square root of, let's say, 2 d of t, eta of t. But this is a time-dependent thing, okay. This is the multiplicative noise. And for that, you have to interpret whether, when you discretize this equation, whether it's whether you take it at t minus, at time t, this is t plus delta t, whether you take this, that's Ito, and if you take, for example, evaluate this as the midpoint, that means t plus delta t by 2, that's Stratanovich.
So what I'm saying is, if you start with the discretized time,
Yes.
with Ito, will it still go to that universal Brownian?
No, universal Brownian thing will just go for Markov additive noise. No, you have to, each problem, each process has a different thing. Discrete things is just a Markov jump process with additive noise, okay. Let's not complicate things. That certainly will go to Brownian. Obviously, if you add, all kinds of different noise, it will not go to, or not all processes converge to Brownian motion, okay. We make a break, yeah. start. Okay, so what I'll do now, so I discussed, several observables like value of the maximum extreme value, or the time at which the maximum occurs in records, etc. So now in this today's second lecture, so what I'll discuss is the time, the statistics of the time. So once again, we have this time series. That's a general picture. So far I was talking about the value of this, the value of the x max, okay, which is the maximum value. But you can also ask, what's the distribution of the, the time at which the maximum occurs? So that is this T max, let's call it, time at which the maximum occurs. In discrete time, of course, this is an integer, but in continuous time it will be just a continuous number. So the T max is also a random variable. So like in the temperature context, you can say which is the hottest day or something. So it fluctuates from sample to sample. And we want to calculate its distribution, statistics, etc. So once again, general structure is that you have a joint distribution of these variables. So given this joint distribution, what can we say about the statistics of T max? Or T med, if you like, minimum time at which the minimum occurs, same thing. But let's just do one thing, statistics of T max, okay? And again, I'll consider these two models. Model one is this IID model, where these variables are uncorrelated. And the second model is this random walk model, which is strongly correlated. Where, as you saw, that the joint distribution of x1, x2, x3, xn in terms of the distribution of the noise, f of eta, so this was just so these are the two examples I'll just work out, and we want to know what is the distribution of the T max, okay? So model one first, let's start with model one, IID. So IID case, this is actually trivial, okay? So I'm asking what is the probability, let me see what's the notation I'm using. Yeah, I'm asking what is the probability of T max given n. So IID model, you see that any of the variables can be maximum, right? You have n variables, they're all distributed exactly identically and there is no correlation between them, okay? So therefore, if you ask which guy is the maximum, it can be any one of them, right, with equal probability, okay? So therefore, the answer is trivially 1 over n. Is that clear to everybody? Because I have just n variables, all of them are equally distributed, and I'm asking which guy is the maximum. could be any of one of the guys, right? So it's just 1 over n. Okay. If you want to formally prove this, then let's try to formally prove this, because this is useful. So what I'll do, so you calculate the joint distribution of the maximum value. So this is the value of the maximum, and its time of occurrence, given n. So what is this object? So each of them is distributed by P of x, right? So suppose that one guy is a maximum with a value x max, right? Because if one guy is a maximum, it has to take the value x max, then this has to be P of x max. And then all the other guys, they have to be less than x max, and there are n minus 1 of them. But this guy who is maximum can be any one of the guys, so there's a factor n here. This is exactly, you take the cumulative distribution and take a derivative with respect to x max, that gives you this answer, right? And so notice that here, the T max, doesn't appear explicitly, clearly, okay? Because it can be any one of them. So therefore, P of T max, this end is not there, sorry, yeah. This is because I'm fixing the x max basically. I'm saying what is the probability that maximum, one guy is maximum, so that is P of x max. Given this x max, and all the other guys have to be less than this, okay? So therefore, the marginal distribution of T max, given n, is just I have to integrate over the x max of this object. Now, this integral looks quite complicated, but if you just make a change of variable, you call it if I take a derivative, so you see the du dx max is just P of x max. Okay? So then, Px max dx max is just du. So you have du, u to the power n minus 1. And what are the limits? When x max is minus infinity, u is 0. When x max is plus infinity, because this is normalized, u is 1. And therefore, this is equal to 1 over n. Okay? So the T max, therefore, probability distribution of T max, if I like, it can take any value between 1 to n, and it has equal probability, uniform distribution. Okay. So for IID variables, any day can be the hottest day, basically, okay, if there is no correlation. So obviously that shows the temperature data clearly is very strongly there must be correlations. It cannot be IID, because otherwise any day could have been the hottest day. That's usually not the case. Okay, so this is this. For IID, it's very, very simple. Okay, almost trivial, and similarly you can calculate, for instance, the probability of the T mean, and again by the same token, this is also 1 over n, because any one of the guys can be minimum. And you can actually calculate the joint distribution of maximum and minimum. And this I leave it as an exercise. It's quite interesting computation. Show that course, Tmax cannot be equal to Tmin. I mean, because by definition, your maximum cannot be minimum. So this is clearly 0, obviously. But if you take Tmax different from Tmin, then the correlation between them, distribution, joint distribution is given by 1 over n into n minus 1. Okay. So this is, again, sort of easy to prove. I mean, again, you write down joint distribution of x max. So you just put one guy as x max, one guy at x min, and this integral should be between x min to x max. Okay. And so what I mean is this joint distribution of x max, t max, x min, t min. This is just p of x max, p of x min, and then so you fix one guy at x max, you fix one guy at x min, and the rest of the guys, they have to lie between x min and x max, and there are n minus 2 of them. Okay? And then again you integrate over x max and x min, and again use this same change of variable, and that gives you the marginal distribution, joint distribution of T max and T min to be this formula here. Okay? So for instance, I mean, interesting thing is that if you calculate T max, the cross correlation between T max and T min. So this is you asking that the day, so T max is the time when you want to, in the context of finance, this is the time when you want to sell your stock, and T min is the time when you want to, buy your stock. So then they are, because they, T max and T min, they cannot be equal, okay, at the same time. So that means there's some kind of effective anti-correlation between them, and you can calculate this anti-correlation. And this is exactly, just again show it from this simple formula. So once again, these are universal. I mean, they do not depend on P of x. So, and there is this negative sign here. It means anti-correlation, because T max and T min cannot be very close to each other. Okay, there's kind of effective repulsion between them. And so if the maximum occurs at some point position, then most likely the minimum is not nearby. I mean, it will be somewhere else. Okay. So there is some kind of anti-correlation between the T max and T min, and this is given by this universal formula here. And then this you can compute just because you know the joint distribution, so from this you can compute. Yeah. Sorry? No, because that will be there if you are interested in just the marginal distribution of x max. Okay, then it could be any n of them. Okay, but here I'm saying that what in a given sample, what is the probability that the maximum has value x max and the minimum has value x min? So maximum, of course, has been achieved by only one guy. Okay, and minimum by one guy, and so so there is no extra factor, of n into n minus 1 here. It's just these two guys. One guy is maximum, one guy is minimum. Okay, and then I'm asking, because you are fixing T max, I mean, you are saying that you are specifying the T max, conditioning on T max and T min. So therefore, there are only two guys there. Okay, and then you have to, by integrating out the other things, marginalizing things, you can actually compute the distribution of T max, T min. Okay. So for instance, I mean, in this formula here, this guy, I mean, or even here, I mean, so yeah, this guy here. So if I want to calculate the x max, okay, just the marginal distribution of x max, I have to integrate over T max. But T max can be from 0 to, 1 to n. So when I integrate over T max, since T max doesn't appear here, you get a factor of n here, right? And that's the combinatorial factor, because you're not fixing T max, okay? You're integrating over T max. Okay, so you can also calculate the distribution of the time difference between T max and T min, right? And this is in the, again, financial context, this is quite important, because this is like you're asking that how, suppose that you buy a stock at T max, and then you want to sell, how long should you wait before you sell your stock, right? So that's the time. And again, knowing this joint distribution, you can actually compute the distribution of tau. I can give you the result, but let's not, okay, I mean, it's a little bit detailed, so it's an interesting result, but you can work it out, it's simple, okay. So this is the I. So IID case basically nothing to do, it's very simple, it's just uniform distribution. But still there is this kind of anti-correlation between Tmax and Tmin, and it's quite interesting to see that. So now I'll go to random walk example, model 2. And there you will see lots of interesting things. But the fact is, again, for IID variables, again, this is all the statistics of Tmax and Tmin is again completely universal. It doesn't depend explicitly on this P of x. No matter what the P of x is, you always get the same result. So once again, we have our random walk starting at the origin and making jumps like that. So I go up to n steps and I look at the maximum and I ask at which step the maximum occurs. So this is the Tmax. So how do I calculate that? And we have this xn equal to xn minus 1 plus eta n. Again, eta n's are drawn from some symmetric and continuous distribution f of eta, and I start from the origin. So that's my problem. I want to know what is the statistics of Tmax. So now you will see that I can derive the statistics of Tmax just from the knowledge of what we did in the last lecture, okay? In terms of this restricted Green's function that I mentioned. How do I do that? Okay. So suppose that I call Tmax as a step n, I call this n. So this is I'm looking for probability that the maximum occurs at step n. Okay. So you take your trajectory. So by definition, this is maximum, right? That means that from starting at 0 up to step n, you have arrived at this value, and suppose that the value of the maximum is x max. And I also call, so I'm looking for the event, just for simplicity of notation, that x max, I call it x, and T max, I call it n. So I'm asking for the probability of this event. So this is the x max equal to x. So what I want to compute is the joint distribution of no, actually no. Let me call it m. Sorry about this because my notations are sometimes okay. And you see this guy. So this is m. So I want to compute, and the end point. Suppose I arrive at some point x. I have to again integrate over the final position. Okay. So I want to compute. So if I ask what is the probability that the trajectory is starting at the 0, it arrives at the maximum value, m at step n. So this is the joint distribution of the maximum and the time at which the maximum occurs, and that finally it arrives at some position x given n steps. So if I know this, then I can just integrate over dx. And this final position has to be anything between minus infinity up to m, because it cannot be bigger than m, because you have already said that maximum has value m. So therefore, this varies over this range minus infinity to plus infinity. So if I integrate this guy, so this is my joint distribution of x max equal to m and t max equal to little n given n. So my goal is to compute this joint distribution. So for that, it's preferable to keep this x as free and finally integrate over this, just like we were doing for the restricted propagator before. Okay? So I want to compute this guy first. So what is the probability that the trajectory starts from here? It arrives at m at step n, and then it arrives at x. So again, if you look at the trajectory, this is level m. So you see on the left part of n, from 0 to n, so you break it into two parts of the trajectory. So on the left part, you have a path which starts at origin, it makes random walk and it arrives exactly at step n to a value m, but before that, it does not cross the value of m, because maximum occurs at exactly n, so therefore it has to stay below m and arrive at m exactly at step n. And on the right part, it starts from there, and then it has to stay below that level up to step capital N minus little n, okay, with the final point as x. Okay. So therefore, I can decompose this path into two bits, left and right, and because they are Markov process, so left doesn't talk to right, so I can just take the product of the, so this will be product of these two propagators basically. Okay. So let me write it down first. So what is this? So this is the, so let me write it this way. N minus n. So this is the left part, and this is the right part. So on the left part, P and M is exactly what I said, is the probability that you start from the origin and you arrive at M at step n, but staying below the level m up to the n steps. But again, and the right part is precisely what I said, it starts from here and it arrives, okay, so now let's think of the left, for the moment forget the right part, look at the left part, P and M. Now this object, again, if I do the same reflection principle, that means I put my origin there and I look downstairs, and then I shift my time step here. So what you see here is, therefore you have a walker which is just time reverse path. Walker which is starting at the origin and staying positive, okay, and arriving at M at step n. Okay? So P and M, therefore, I'll first write it down and you have to convince yourself that this is true. So P and M is just whatever we had calculated G plus of M and starting at the initial position 0, step n. Is it clear? Because if you just put yourself here and forget about the right part, put yourself here and just look at this time reverse path. Okay. So what you see is that you have a random walker which is jumping from here to there, and it arriving here. So from that reference point, this distance is m. So you are starting at the origin and you are arriving at m, but staying positive, meaning because you are looking at this way. Okay. And that is exactly our restricted propagator. That is, you are arriving at m. So this is like what I'm saying is that the left part is that you have a walker which starts at the origin and it just arrives at m after little n step. Because if you see from that point of view, I mean, or just reflect this and look at in the opposite way, time going opposite way, we are going up to 0 to n steps. And so this is exactly that. So this we already know. Now what about the right part? So this is the left part. Right part, same way. I go up there and I see from this point of view. So I have a random walker which starts again at the origin, because this is my level at the origin. And it goes there, jumps, it stays positive again, and it arrives at, from this point of view, this distance is m minus x. So this is right part, what I call p n minus n m minus x. This is just g plus of arriving at m minus x, starting at 0 in step n minus x. So therefore, this object, you just have to convince yourself a little bit. I mean, just if you draw a picture, you will see immediately. Yeah? No, because I have shifted my origin here. You are putting yourself there. This is the origin, right? Then, and this is the origin, and this is the positive side, if you like. Just reflect the path, okay? And then you think of from this point of view, you are going that way, and this is the positive axis. So you are making a jump, 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 jump. You are arriving at m minus x, starting at the origin. You are arriving at this point, right? So it's m minus x, and this is your new origin, if you like. So this is just this propagator. Okay? So therefore, what you have okay? And now, I want to integrate, so this is this, so I want to, so from this first I want to integrate over x, going from minus infinity to m. Because this guy doesn't have any x in it. And now you see that if I make a change of variable, so when x goes to minus infinity, it goes to plus infinity, and when x goes to m, it goes to 0. So, but this object, you see this is exactly what we had computed, right? So this is, you start at the origin and you reach y without crossing the origin up to n minus 1 steps, and then integrating over all the origin. So therefore, this is just, in our previous notation, this is just q survival probability starting at 0 up to step n minus n. And we know this answer. This is given by the Sparr-Anderson theorem, right? Remember that Sparr-Anderson theorem was q 0n, stu n, choose n, 2 to the power minus 2n. And now I want to calculate the probability, marginal distribution of n. So this is the joint distribution of m and n, if you like, given capital N. And I want to calculate the distribution of the time at which the maximum occurs. So this is just integral 0 to infinity p mn n, because m has to be bigger than or equal to 0. And now this guy is independent of m, so you just have to but now you look at this guy here, okay? This is exactly same as this, except that n minus n is replaced by n. So this is again just q 0n times q 0 n minus 1, n minus n, sorry. And this is exact results. So what you have therefore, it's really beautiful, and you will see that this will give us a very, very simple proof of this Power-Anderson theorem. So what do we have? So we have probability distribution of the time at which the maximum occurs, given that you have a total number of n steps in the random walk language. So this is therefore q 0n q 0 n minus n, and so therefore by Power-Anderson theorem, Power-Anderson theorem tells you, because we know this expression, so we are just writing down this. So this is so this is the exact result for a random walk or Levy flights, whatever. This is again totally universal result. It's the same result. It's universal for any single n. So that means probability that the time of maximum occurs, let's say step n, is given by this exact universal formula. And here we used the fact that q0n equal to this, and I told you that this is the result of Power-Anderson. But this actually, you can use the same technology just to prove this Power-Anderson theorem. Because you see, from this, so far, I mean, up to this step, I did not specify yet what is q0n and what is q0n minus, or what is q0n, right? Only thing we know that quite generally, just by path decomposition, the probability that the maximum occurs at step n, this is given by the survival probability of the walk starting at 0 up to step n times the survival probability of the walk starting at 0 up to n minus 1 steps. Okay, so Power-Anderson tells me the answer, so we get the answer. But I mean, suppose I don't know this Power-Anderson result, okay? But this is exact, irrespective of whether I know the survival probability or not. But now, you can use this result to prove this Power-Anderson. And this is beautiful. You see, what happens is that this is true, and now this is a n. Now what is the n, range of n? N lies between 1 and capital N, right? Because the maximum can occur at any of these steps, 0 to n actually. So what I'll do, I just consider the generating function. So, okay, you know that one thing, therefore, you know, this is a random variable given capital N. So if I sum over n equal to 0 to n, this is just 1. It has to be normalized. Okay? So, if this is true, then you see that immediately that, so if I just substitute this result there, okay? But this has a kind of, sorry, this is little end. This has a convolution structure. So if I take a generating function, so if I call q0n s to the power n as q tilde of s. So if I multiply this guy by s to the power n and sum over n equal to capital N, sorry, 0 to infinity, then you see that both sides have to multiply by s to the power n and sum over n equal to 0, 0 to infinity. So because of the convolution, so we have q tilde of s times, this is also q tilde of s, and when you take multiply by s to the power n and sum over n equal to 0 to infinity, this just gives you 1 over 1 minus s, right? Simple geometric sense. So q tilde square is 1 over 1 minus s, and therefore q tilde s is 1 over square root of 1 minus s. And if I expand in power series in these things, you get q0n equal to 2n choose n, 2 to the power minus 2n. So this is the simplest proof of Sparr-Anderson theorem that I know, okay? And I told you, people have tried many, many different techniques. So this was the result actually we derived with Philip Munex and Gregory Scher. And as I mentioned, many people actually have looked at Sparr-Anderson theorem, tried to prove by different techniques because the result looks very simple. But in most of the papers actually resulted in having a more complicated proof. But this is just from the normalization of the Tmax basically, okay? And so this is a very, very simple proof. So you know now Q0n, and you substitute this there, and you get this result. And this was again also derived by Sparr-Anderson. So two things. So first of all, it's again universal. It does not depend on the jump distribution of your random walk, okay? And it has this particular form, okay? And now comes this interesting thing. So you can plot this function as a function of, little n. But I think interesting thing is it's universal for any little n basically and capital N. But its interesting thing is that if you take so suppose I take the n goes to infinity limit, capital N goes to infinity limit, and keeping n over n fixed. You just look at on a scaled way basically, okay? So then you can use this Starling's formula. So Starling formula, you know that n factorial, basically large n limit, goes like square root of 2 pi n So if you just use this Starling formula, just expand this guy, keeping little n over capital N fixed. Notice that this scaling function, or x if you like, n over n, this is between 1 and 0, right? Because the Tmax can be anything between 0 to n. So the ratio n over little n has to be bounded between 0 and 1. And this I leave it as an exercise. If you work it out, so you keep this ratio fixed to be x and take the large n limit. And then it actually goes into a scaling form, which is, okay, so let me call it some other function, I don't know. Let's call it h. Okay. And this function h of x, with x supported between 0 and 1, has a very simple form. Okay. And this is called Levy's arc-sine law. Why is the arc-sine? Why is it called arc-sine law? Because if you just look at the cumulative distribution, then this is just 2 by pi sine inverse of square root of z. So that's why it's called cumulative distribution as the arc-sine form. So this is the function. So therefore, if I plot this guy, So x, remember, is just if, at what time between 0 to capital N that your maximum is occurring. So x is just, n is a random variable, n over n. So it's between 0 and 1. And if I plot this function h of x, you see it diverges at the two ends. It has a U-shaped form. See, many distributions, typically like Gaussian distribution, it has a bell-shaped form. That means the maximum of the PDF occurs near the mean. But here the mean, mean time at which, if you take the average value of this, just compute the average n here with this PDF, this will be n by 2. So that means average x is actually half. So that's what the average is. But the maximum of this PDF does not occur at the average. So is the two n values, x equal to 0 and x equal to 1, they are more likely. That means the probability density has two peaks at the two ends, 0 and 1. So what this is very unusual. What this means is that for Brownian motion, okay, for this walk actually, for not because this is, again, I insist that this is not just although Levy originally proved it for Brownian motion, but this scaling limit result holds for any random walk, even including Levy flights, okay? Because this is a result which is totally universal, independent of the jump distribution. Okay, so it's much more general than Levy's arc-sine law. Levy's arc-sine law originally derived from Brownian motion, okay? But this is a much more general result. This universal scaling function, h of x, and so what it means is that your walk in this large n limit, so it starts at the origin. So what does mean x goes to 0? That means your n, the maximum, occurs near 0. Maximum occurs near 0, that means that the walk, in a trajectory, the events that contribute to that event, the trajectories that contribute to that event, the maximum is occurring right in the beginning. Okay, n goes to 0 is that kind of event. So that means the walk more or less stays on one side. So that means such walks where the walk stays on one side of the origin, let's say negative side, so they have a higher probability density corresponding to typical paths. So typical paths will be, of course, when you have many crossings and things like that, okay? But these kind of paths have more probability density, and similarly, x equal to 1, when x goes to 1, that means n goes to n, that means the time at which the maximum occurs is almost at the end, which means, the Tmax occurs somewhere there. So maximum is somewhere there. Of course, it doesn't say that, it has to be, it can be going like this, but basically maximum occurs. So these kind of paths also have very high probability. So what it says is that such motions are quite stiff, this random walk motion. Stiff in the sense that if it goes to one side of the origin, it tends to stay in that origin. So even though, on an average, it will cross many times like this, but if you, take many samples, you will see that many, this is probability density, of course, not really full probability, but these paths have higher probability density compared to such typical paths, okay? So this is a very unusual kind of distribution, and this is what is reflected by saying that rare paths, like x equal to 0 or x equal to 1, have higher probability. These are rare paths, okay? But these rare paths have higher probability density than the average path, which corresponds to x equal to half. Okay? So this is a sort of intricate property of such random walks, and in particular, which includes Brownian motion as a special case. But and this kind of gets reflected by studying the statistics of the time at which the maximum occurs, and so this is very, very nice. And then same thing, you can actually calculate the time at which the minimum occurs. Okay, T-mean. And T-mean, probability that the T-mean equal to n given n will have the exactly same result, because the maximum, and this is a symmetric random walk, so it will be exactly the same result as sparseness. And but then you can actually try to calculate T max minus T mean. As I said, this is the, or maybe T mean minus T max, doesn't matter. I mean, T mean minus T max. Because as I said, the random walks often in finance, they are used as a model for stock prices, some special limits. So this is called the Black-Scholes model. And there you see Tmax is the time at which you want to buy your stock, and Tmin is the time at which you want to sell your stock. So this is therefore the time you need to wait before you buy a stock, and how long do you have to wait to sell your stock, or vice versa. So that is the distribution of tau. And this one, for general random walk, I mean, it's because you need to calculate the joint distribution of Tmax and Tmin from that. So for general walk, it's not so easy to do that. You can do the calculation. But in the Brownian limit means again when the variance sigma square is finite and you take the large n limit. So in the Brownian limit, you can actually compute this distribution. Okay? So individual marginal distribution of Tmin and Tmax is given by the arc-sine law with the Brownian case. But the time difference actually has a quite non-trivial form. I'll just write it, but I will not give you the derivation of these results, but just to tell you that how complicated it is. Okay, so again, I mean, like in the IID variables, here again, you can, okay, this is exact, and so let me calculate in the Brownian limit. If I calculate exactly this correlation function that we calculated already for IID variables. And with that, I'll finish. So this turns out to be the exact result is 7 times zeta 3 minus 6. It's quite non-trivial, over 32 times t square. No, it's some number. So this is a result that was derived by Francisco Muri, who was my PhD student, myself and Gregory Share. This is quite a recent result, actually, it's 2020, something like that. Okay. But not only that, so again you see the anti-correlation, like in the case of IID variables, there it was, you know, minus whatever, n plus 1 over 12. And here you see that the Tmax, that's quite normal, because if you have a Tmax somewhere, Tmin cannot be very close by. There's a kind of effective repulsion between them. There's an anti-correlation. And so there's this anti-correlation which shows up, and you can actually compute this explicitly. And the distribution of the time difference, so let me just state the result without proving. Again, you can use this path integral method to compute this. So what you find is that the P, so this is exactly in the same paper that with Francisco Muri, as I mentioned. So this again has a scaling form, which is 1 over T into, okay, let me call it FBM here, of tau over T. So this tau is the time difference, T max minus T min. How long do you have to wait? Okay. And this scaling function is highly non-trivial. My eyesight is getting bad. So it's a pretty non-trivial function. So it has these asymptotic behaviors, which is, if you plot this function, it looks like this. So FBM of y versus y. So y, of course, cannot be bigger than +1 and cannot be less than -1. It's symmetric around y equal to 0. And it has this behavior when y goes to 0, it goes like 8 over y squared. So there's a sort of tapering essential singularity here. But strangely enough, when y goes to 1, it always goes to half. Yeah, this value is half. So this was again the result of Mori et al. And so you see that this is a very, even for Brownian motion, this result is very new. I mean, it was not known before. And this is an extreme statistics thing. And this same scaling function also appears in other problems like fluctuating interfaces and so on. But very, very non-trivial result. Okay? And from that, you can calculate all the statistics of tau, its variance, moments, etc. I mean, knowing this function exactly. And so this is the distribution of Tmax. So main point I'm trying to say is that, again, I mean, you see that this is due to the strong correlations between the x's in the random walk model as opposed to IID variables. IID variables, this is quite trivial to compute this. But for Brownian motion or random walk or Brownian motion, this is already highly non-trivial function. And so there's a lot of interesting results to derive even for, even in this sort of very simple random walk results and a lot of universal results and so on. And so the main point is that not just for extreme values that we have already discussed in the previous lectures, I mean, even the time at which the maximum or minimum occurs has very interesting statistics. Okay, so that's what we see from here. Okay, and so what I'll do in the next lecture, I mean, I have 2 lectures left only. So I'll just do the record statistics as the last thing a little bit. And those, again, I mean, if you are interested in details which I could not present here, you can have a look at this book. Okay? So, okay, I think I'll stop there. Thank you.
So I have one question.
Yeah.
So if I think of the number of zero crossings between 0 and
Yes.
x, what does that distribution look like? Is it peaked in near the middle or towards 0?
No, so, okay, I mean, for random walks, okay, I mean, if you just discrete time random walks, okay, if you ask what is the number of zero crossings, so that you can actually compute, so that effectively has a Gaussian peak. So you can calculate the average number and it will be peaked around the average. Okay. But when you take the Brownian limit, then of course it's very complicated because you see, as I mentioned, if it crosses 0, it crosses infinitely often. So if you actually calculate the average number of zero crossings in an interval small t, delta t, it actually scales like delta t to the power half, not as linear in delta t. Which means that the density, that is, if you divide by delta t and take the limit, it diverges. There is a huge number of jittering zeros. And that's why, it's, for Brownian motion, you cannot really, I mean, you have to be very careful, I mean, you have to put the real boundary conditions to look at the trajectories. But in random walk, you don't have that problem. I mean, it's a discrete time random walk is perfectly, it's a kind of much more regularized walk, basically. Okay, so then we'll meet tomorrow. So, you sleep well.